Hello student, welcome back to the course on optimization methods for civil engineering. So in today's class, we'll learn how to solve a nonlinear optimization problem using Excel solver. So we have already solved a linear problem using Excel solver, and today we'll see how we can solve a nonlinear problem with constraint using Excel solver. So let us see. So we'll consider a few example problems, and then I will show you how you can solve a partial differential equation using Excel solver. So this is the first problem I will consider. This is a two variable problem. So we have x1 and x2, and there are two constraints in this particular problem. So the first constraint is a linear constraint and second one is nonlinear constraint. So the solution is 1 1 and I should get the optimal function value is minus 1.1. So this problem we have already solved using R software. So you can see that this is the constraint solution of this particular problem, and I should also get this particular solution when you are solving this problem using Excel. The second problem is also a two variable problem. So we have a nonlinear objective function. So we have a nonlinear objective function. So this is your objective function, and we have two constraints here. The first one is linear and second one is nonlinear constraint. So here I should get this particular solution, and somewhere here this is the constraint solution of this particular problem. So we have also solved this problem using R. So let us see whether we are getting the similar result in Excel. The third problem is also a nonlinear problem with one linear constraint. So objective function is nonlinear, and if you are solving this, then you should get this particular solution, and somewhere here is the optimal solution of this particular problem. So I will try to solve this problem, and the fourth one is a little bit complicated problem to solve using classical optimization technique, but let us see whether we are getting the solution using Excel solver. So we have already solved this problem using genetic algorithm, and we got the constraint optimal solution of this problem, and the solution is 0 and 1.5, and objective function value is 8.4933. Okay. So here this is the objective function, and we have two constraints. Okay. So this is first constraint, this is second constraint, and x1 x2 are positive and range is between 0 and 5. That means x1 is between 0 and 5 and x2 is also between 0 and 5. Let us see how you can solve a partial differential equation using Excel solver. So I will show you, you can use the optimization technique for solving a partial differential equation. Here I would like to solve a partial differential equation using Excel solver. Then this is related to the flow equation. So this is nothing but the flow equation for homogeneous isotropic confined aquifer. So if you have gone through groundwater hydrology, so I think you have seen this particular equation. So this is the flow equation for the case of homogeneous and isotropic confined aquifer. Okay. So this is the equation here. So this equation is T del square phi by del x square plus T del square phi by del y square plus n. So this is the source term, and this is equal to 0. So I would like to solve this equation using Excel solver. Here T is the transmissivity of the aquifer, the unit is meter square per day, and del square is the Laplace operator. phi is the hydraulic head, so that I would like to calculate, and N is the pumping or resource value. So, this is the source term and unit is meter cube per day meter square. So, how I am solving this equation? So, I am solving this equation using finite difference approximation, okay, of this 2D flow equation, and I am not showing how you can do the finite difference approximation, but if you are applying finite difference approximation, so finally you will get this equation, okay. You will get this equation, and I would like to solve this equation, and where A equal to T by del x square. So, this is the grid size, and B equal to T by del y square. So, this is the grid size, and del x and del y is the grid size in x direction and y direction. So, how we will solve this equation? So, what I will do basically, so let me go to the next slide and then I will come to this particular slide. So, in this case the boundary values are known. Let me explain how we will solve this problem. So, let us consider a rectangular aquifer. So, idea is that I would like to find out what is the value of phi at each grid point. So, entire aquifer, so this is the aquifer and we have divided into some grids, and on the left side this is constant head boundary and we know what is the phi value here, and right hand side this is also constant head boundary. So, we also know the phi value here, and on this side, so this is no flow boundary, that means the gradient is del h by del y is 0, and here also del h by del y is 0. Okay. So, we know this thing. Now, I would like to calculate the value at each grid center. Okay. So, that means whatever finite difference equation, so this is the finite difference equation. So, this has to satisfy at each grid point. So, if I write the finite difference equation, suppose I am writing equation 1 here, equation 2 here, and this is 3, 4, 5, 6, 7, 8, 9, 10, and this is my 100 equation. So, I will get total 100 equation, and if I solve this 100 equation, then I will get the solution of this problem. So, if I can solve all these 100 equation, then I will get the solution of this problem. So, what I am doing here, I am formulating an optimization problem. So, and this actually, so this is the equation that has to be satisfied, at each grid center. Now, for any arbitrary value, so right hand side will not be equal to 0. So, I am considering this is Eij. So, Eij is the error. Now, I have formulated an optimization problem, that means I would like to minimize this error. Okay. So, here grid size is I equal to 1 to 10 and j equal to 1 to 10. Okay. And basically, so I am getting Eij, and I am just squaring it just to make it positive. So, because this error should be positive, I would like to minimize this error. So, I am squaring it, or you can also use the absolute value. So, either I can write Eij square or Eij, okay, absolute value. So, both are okay. So, I will use this one here, and this is Eij, and this should be equal to 0. But what I will do, I will make Eij less than equal to some absolute value. Okay. So, maybe this is 0.001 or 0.0001, something like that. Okay. So, it will not be 0, but it will be near to 0. So, I will solve this problem using Excel solver. So, what I will do, I will use this particular equation. Now, let me go to the next slide. So, here this is the value given, that T equal to 300 m square per day, okay, meter square per day. So, I have used del x equal to 100, del y equal to 100, and the aquifer size is 1000 by 1000. So, this is 1000 meter and this is also 1000 meter, and I have divided in grid, and one grid size is 100 by 100, okay, and I have used T equal to 300 meter square per day. Okay. Now, in this case, in my case, so del x equal to del y, just to simplify the problem. So, you can also use different del x, del y, but here I am considering del x equal to del y. So, if you are doing that, so that means A equal to B, and if I put A equal to B here, so finally what I am getting that this will be your A, this will be your A, this will be your A. Okay. So, then if I divide this particular equation by A, so I am getting this equation, that is phi I plus 1 j, then phi I minus 1 j, phi I j plus 1, phi I j minus 1, minus 4 I j, and this is n I j. And finally, so if I put what is the value of A, so A is T by del x square. So, what I am getting that n into del x square by T. So, this is nothing but the pumping value, that is in meter cube per day basically in this case. Okay. So, this is the pumping value, that is the source term you are telling, that is the source term, and finally I am getting this equation. Okay. So, I am getting this equation. So, I will use this equation here. So, basically using this equation I would like to solve the problem. Okay. So, I will also explain. So, I will directly go to Excel and I will show you how you can treat this particular problem or how you can solve this particular problem using Excel solver. So, this is the Excel, I should get finally this is the solution of this particular problem. So, I will explain you, and this is the surface plot I have done, and there is some pumping here, here, here and here. So, with this pumping, so you should get this is the value of H. Okay. So, I am getting somewhere here. So, I will solve this problem using Excel solver. So, now let us go to Excel solver and see how I can solve all this problem using Excel solver. Now, let us consider the first problem. So, in the first problem we have an objective function. So, this is the objective function, and objective function is x1 minus 2 whole square plus x2 minus 1 whole square, and we have two constraints, and these constraints are inequality constraint, that means less than equal to 2. So, what I will do, I will define the variable here. Okay. So, I will define the variable here. So, this is the variable, and we have two variable, that is x1 and this is x2. Okay. So, this is x2, and you consider some initial value. Let us start with 0. I would like to start with 0 here. So, these two are my variable. Okay. So, I am using these two variable. Okay. And then let us write the objective function here. So, objective function is, so I am writing here. So, let me write the objective function. So, this is objective function, and objective function is, I am writing f1 here. So, write the objective function. What is objective function? Objective function is x1. So, this is x1 minus 2. Okay. So, this is square plus x2 minus 1, this is square. Okay. So, this is my objective function. So, I am defining objective function here. So, I am getting for x1 equal to 0, x2 equal to 0, objective function value is 5. Okay. Now, you write constraint. So, we have two constraint here, that is z1. So, you write z1, what is z1? z1 equal to x1 plus x2 minus 2. Okay. So, g1 value for x1 equal to 0, x2 equal to 0, this is minus 2, and you also write z2. So, z2 is x1 square minus x2. Okay. So, it is 0. So, I am defining the objective function and constraint here. Okay. So, I have defined my problem, and this should be less than equal to 0, is not it? Less than equal to 0, and this should be less than equal to 0. So, this is my constraint. Okay. So, now let us go to Excel solver. So, just see whether Excel solver is here. So, there is no Excel solver here. So, then what I will do, I have to install that one. So, you go to option, you go to add-ins. Okay. So, you go to Excel add-ins, and Excel, within Excel add-in, so you will get solver add-in. Okay. So, you just check this particular box and click OK. So, it has been installed, and you can see that on the right hand side the Excel solver is there now. So, this is under data. Okay. So, under data, this is the Excel solver. So, let me go to the Excel solver. So, already you know that one. So, what I will do, I will delete this portion. Okay. So, I will delete this, I will delete this portion. So, I will start from the beginning. Okay. So, here I have to define the objective cell. So, objective cell is this, and I would like to minimize the objective function. So, I have selected minimization, and if your problem is a maximization problem, so you can select maximization, or if it is a value of, then you can also select this one. So, here I have to define the cell, that means my variable cell I have to define. So, here these two are my variable cell. Okay. So, D3 and D4. So, that is my variable cells. Then you define the constraint. So, I have two constraint here, these two cell basically, and this should be less than equal to 0. Okay. So, now I have defined the optimization problem here, and so you can make unconstrained variable non-negative. So, you can this, and I will use mainly simplex, sorry, I will use ZRG nonlinear method. Okay. So, that I will use. You can change the option here, but I am not going to change right now here. So, I will use the default value and just see whether I am getting the solution or not. Okay. So, let me run this particular, or by I can execute this particular solver. So, using the solve button. So, let me solve this problem. Yeah. So, solver results, solver found a solution. So, solver found a solution, all constraints and optimality conditions are satisfied. Okay. So, I can see the answer here. So, you go to answer and just see the answer. So, this is the answer report, and you can see actually. So, here I have used ZRG nonlinear, solution time is 0.032 second, and there are some other data about this particular algorithm, and you can see the objective function value is 1, then x1 is equal to 1 and x2 equal to 1. So, it is almost 1, that is, yeah, here it is 0.999 and here it is 1.000011, something like that, and both the constraints are satisfied. Okay. So, you can see that one. So, this is the solution of this particular problem. So, I can also see here. So, I am getting this solution now 1 1 and objective function value is also 1 and all constraints are satisfied. Okay. So, if you go to this particular problem here, so just see, so this is the first problem and the solution is the solution is 1 1. Okay. So, the solution is 1 and 1. So, here also I am getting 1 and 1. Okay. Okay. So, this is the solution of this particular problem. Okay. So, I am getting this particular solution. So, I hope this is very simple. So, I can easily solve. So, without programming I can solve a nonlinear problem here. So, you need not go for any programming. So, you need not download MATLAB or R programming here. So, if you have a simple problem, so that can be solved using Excel solver. Okay. So, let me go to the next problem. In problem 2, we have two constraints and an objective function is not nonlinear. Okay. So, let me write it. So, I would like to copy this thing. So, this is, we have two variables, that is x 1 and x 2. So, I am putting x 1 equal to 0 and x 2 equal to 0, and here objective function is 3 star, that is 3 star x 1 square minus 2 star x 2, okay, 3 x 1 square minus 2 x 2. Okay. Then you define the constraints. So, constraints are, the first one is 2 star x 1 plus x 2 and minus 4. So, if I write minus 4, that means less than equal to 0. Okay. And second one is x 1 square. So, this is x 1 square plus x 2 square, x 2 square minus 19.4. Okay. So, here it is less than equality type, and here also this is less than equality type, and this is less than equal to 0, and this is less than equal to 0. Okay. I have defined the objective function and constraint here. So, now I can solve this problem using solver. So, let us go to data, use solve button. So, here you define that this is your objective function cell now. So, this is the cell, this is minimization type, and here this is the variable cells, and so this is the constraint. The constraint should be less than equal to 0. So, I have defined it. Now, let us solve this problem. So, if it is okay and if you have defined everything correctly, so you should get the solution. So, let's solve it. You just see, I can see the report also, and so this is report 2. The objective function value is minus 8.67, and the solutions are that x 1 equal to minus 0.1999. So, that means 0.2, and this is 4.399, and on all constraints are satisfied. So, you can see that one, that I am getting the solution, that is x 1 equal to minus 0.2 and x 2 equal to 4.4. So, this is the solution. You can see on the right hand side the solution is minus 0.2 and 4.4. So, I am also getting the same solution and constraints are satisfied. Okay. So, it is quite easy to solve a nonlinear problem using Excel solver. Let us go to the next problem. The third problem, we have one objective function and one constraint. So, let us solve it. So, before that I would like to copy this portion. So, I would like to copy this portion. Here I would like to start from 0 0 and objective function is x1. So, this is your x1 minus 3 whole square plus x2 minus 3 whole square. Okay. So, So, this is x1, this is x1 minus 3 whole square plus x2 minus 3 whole square. Okay. And we have only one constraint, that is 2 star x1 plus x2 minus 2. Okay. So, this is the constraint, and okay. So, this is the constraint, and this is less than equal to 0, less than equal to 0. So, I have defined the problem here. So, let me go to solver. So, here I can define, okay. So, I can define. So, I can define the objective function cell. So, this is objective function cell, this is the objective function cell, then changing cells are these, then we have one constraint, and that is this, and this is less than equal to 0. Okay. So, let me, so now I have defined this particular problem, and if I solve it I should get the solution. So, let me solve it. Yeah, I am getting the solution. The solution is, you can see the report, solution is 0.2 and 1.6. So, I am getting, and this is 9.8. Okay. So, you go to answer and just see. So, this is 9.8. So, this is actually plus 9.8. Okay. So, I am getting the solution. So, you can see the objective function value is 9.8, and these are the variable value, that x1 equal to 0.2 and x2 equal to 1.6. Okay. So, I am getting the solution. This is your problem 3. So, let me solve the fourth problem. The fourth problem is a complicated problem. So, I have already defined the problem here. So, here I have defined the problem. So, we have two variables. So, variables are x1 and x2. So, this is the objective function value I have defined, and this is the constraint. Okay. These are constraints, and constraints are your less than equality type. That means, this is less than equal to 0, and this is also less than equal to 0. Okay. Less than equal to 0. Now, let me solve this problem. So, this is a complicated problem to solve using Excel solver. So, here every time you may not get the solution. The solution of this problem is, so I have defined here, so just see that you should get 0 and 1.5. Okay. So, 0 and 1.5 you should get. So, let us see whether you are getting. So, 0 and 1.5 is the solution, but let me start with 0 and 0. So, whether I am getting the solution or not. So, you go to data, you go to solver, and the problem I have already defined this problem. So, this is my objective function cell. So, this is objective function cell, and these are the variable cells. Okay. The changing variable cell is these two. So, these two are the changing variable cell, and then we have constraint here. So, let me add the constraint. So, there are two constraints. So, these two are constraint, and this should be less than equal to 0. Okay. Now, let us solve this problem using solver. Just see whether I am getting the solution or not. So, I am putting 0 0. So, no, I am not getting the solution. As I said, this is a complicated solution, and it may be difficult, or it is difficult to solve this problem using Excel solver. Okay. So, I am not getting the solution. Then what I will do, if I am not getting the solution, change the initial point. Suppose I am putting 1 1 now. So, in that case, whether I am getting the solution? No, 1 1 also I am not getting the solution. Okay. So, then you put 2 2. Are you getting the solution? No, you are also not getting the solution with 2 2. Then 2 1, you just see whether you are getting a solution with 2 1. Yeah, I am getting a solution. This is 1.5 and 0. So, this is also a solution, but this is not optimal solution. Maybe this is another local optimal solution. So, you are getting this is 1.5 and 0, but Excel solution is 0 and 1.5, but you are getting 1.5 and 0. So, then what I will do? I will put this is 3 and this is 1, and then you solve it and just see whether I am getting. Yes, this time I am getting the solution, and the solution is 0 and 1.5. So, this particular problem is difficult to solve using the classical optimization technique. So, I have solved this problem using genetic algorithm, and every time I am getting the global optimal solution of this problem. But when you are solving this problem using classical method, so as you have seen, so it is sensitive to the initial solution. So, in some time you are not getting any solution, you are in the infeasible region. Sometime you are getting solution, but that may be a local optimal solution, but once you are changing your initial solution to 3 2, or then basically we are getting the solution. Okay, let me. So, once you are taking 1 and 3 as the initial solution, then you are getting the solution. So, let me try with 1 and 3 again. So, this is 1 and 3 again, and if you are solving, so in that case you are getting the solution, and that is 0 and 1.5, and objective function value is 8.5. So, therefore, when you are applying the classical methods to solve a non-convex problem, so where you have more than one optimal solution. So, in that case what you will do? You change your initial solution. Okay. So, change your initial solution, that is your x naught, and try whether you are getting different solution or not. Okay. So, once you are taking an initial solution which is in the global optimal region, so you may get the global optimal solution of the problem. But if you are applying the non-classical technique, so like genetic algorithm or PSO or other methods, so there is a high probability that you will get the global optimal solution of the problem. So, this particular problem I have solved in the last class using genetic algorithm, and I got the global optimal solution of the problem in a single run. Okay. So, every run I am getting the global optimal solution of the problem. Now, let me go to the partial differential equation. So, I said that I would like to solve this partial differential equation using Excel solver. So, I will show you how you can solve this problem using Excel solver. So, here already I have solved this problem, but let me try again. Okay. So, let me start it from the beginning. So, let me make it square. Okay. And this also I make it square. Okay. So, here let me define my aquifer. So, aquifer size is 10 by 10, that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, this is the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, this is my aquifer. So, I am putting a color here. So, a different color, maybe this particular color, and I would also like to put the grid. So, as you know that left side is your constant head. So, this value is given and this value is 100. Okay. So, this value is 100. So, I am putting this value here, and right side value is also known, and this is the also constant head. Okay. So, this is also given. Now, you consider some initial solution here. Okay. So, let me consider 99 as the initial solution. So, I am considering 99 as the initial solution. So, as you know, when you are applying the classical method, so you should start your iteration with an initial solution. So, in this case, I would like to find out what is the value at its grid point. So, initial solution is your 99. So, as you have seen, so we have total 100 grid point. That means, in this particular problem we have 100 variables. Okay. So, we have 100 variables, that is x1 to x100. So, I would like to show you that how you can solve a problem with 100 variables. Suppose in the earlier problem we have solved, so we have only 2 variables. So, but Excel is also capable of solving a problem having your around means having 50 or 100 variables. So, in this particular version of Excel, so this is the free version. So, there is only one restriction, is that if your problem has more than 100 variables, so you will not be able to this Excel solver. Okay. So, your number of variables should be less than 100, but in this particular problem we have exactly 100 variables. So, I can solve this problem using Excel solver. So, I have considered the initial solution as 99, and I also need to define the boundary condition here. So, here boundary condition is that no flow boundary, and that means the value will be same, gradient value, the gradient value is 0. So, therefore, this cell value will be equal to this cell. Okay. So, that means this is equal. Okay. So, similarly, here also this will be equal. Okay. So, this will be equal. So, I can do that. So, I have defined here. So, let me define so this is the boundary condition. So, this is constant head. Okay. So, I will rotate this text. Okay. So, this is the constant head here, and here also this is the constant head. Okay. So, this is also constant head. This is also constant head, and here this is no flow boundary. No flow boundary. Okay. And this side also we have no flow boundary. Okay. So, this is the boundary values. I am putting a different color. So, this is, and this is also, and this is also. Okay. So, now I have defined my problem here. So, I have defined the constant head. So, these values are known. So, these are the boundary values. So, left hand and right hand side, and here it is no flow boundary, that means gradient is 0. So, I have copied, I have actually make this particular cell equal to this cell. Now, let me define. So, this is the 5 values I have. Let me define the pumping value, okay, that source term here. So, suppose I have a source here and this is around 5000, okay, this is the source, and for others, so this will be equal to 0. So, you can put it or otherwise you need not put it also, okay. So, this is fine. So, this is fine. So, if you are not putting, then also it will consider 0. So, these are all zeros. So, these are all zeros. So, I have only one pumping here. Now, what I will do? I will write the equation. So, which equation I will write? I will write this particular equation. Okay. So, this particular equation I will write. Okay. So, I will write this particular equation. So, let me write the equation here. The equation is this is this plus this plus this plus this minus 4 star Ij plus this divided by T. So, here I am putting so, these pumping values are 0. So, I am putting all 0 and somewhere here it is minus 5000. Okay. So, now let me write this equation. So, I am just copying this equation. So, I am getting this. So, before that I have to put the absolute sign here, ABS. Okay. So, if I put ABS absolute value, so either you can put absolute or you can put square also. Okay. And here I will make sum. Okay. So, total error I am getting 26.67, and I would like to minimize this error in order to get the value of 5. So, let me use the Excel solver. So, you go to data, then you use solver. So, here the objective function is the error function, that is O27. So, O27, and these are changing cells. So, I have total 100 changing cells. Okay. So, all 100 I have considered, and then I have constraint. So, how many constraint I have? I have 100 constraint. Okay. So, these are all constraint, and this should be less than initially you consider 0.01. Okay. So, now I have defined the problem. So, this is the problem I have defined, and just see whether I am getting the solution or not. So, let me solve this problem. If it is fine, then I should get the solution. So, what it will do? It will try to minimize the error. So, you can see it is running, and solver found a solution. All constraints and optimality conditions are satisfied. So, you can see the answer, but before that let me refine or let me increase the precision. So, what I am doing, I am just increasing the precision to 001. So, let me solve it again. So, now you just see, I can see the report. Yeah. So, I am getting a report here, and you just see these are the value. Okay. So, these are the, so original value was 99, and finally, I am getting this, so these values. So, all 100 variables are here, and all 100 constraints. You just see I have total 100 variables and 100 constraints. So, these constraints are there, and all of them have satisfied. So, you just see constraint value is less than 0.001. So, I am getting the solution. So, now this is the solution, and as I have said, this is a flow problem, and there is a pumping cell. There is a pumping cell here, and if I plot it, so I should get the cone of depression. Okay. So, cone of depression I should get. So, I think you have already gone through well hydraulics chapter of water resources. Okay. So, there actually if we are pumping water from the confined aquifer, so when you are pumping water from a confined aquifer, a cone of depression will occur. So, I can see that cone of depression here. So, let me plot it. So, I can plot this surface. So, let me go to this one, and here I can plot it. Okay. So, this is the plot you can see. So, this is the plot you can see, either this is the plot. Okay. So, you can see that this is the plot, and here from here actually I have extracted 5000 meter cube per day, and you can see basically that a cone of depression has occurred. So, that means I am getting, or I got the solution. Okay. So, that means I got the solution of this particular problem. So, you can also see, suppose if I put another well somewhere here, suppose this is minus 2000. Okay. So, pumping is minus 2000, and now error is 6.76. So, I can also minimize this error, just go to data and solver, then I will solve it again. Okay. So, let me solve it again. So, you can see that I am getting I should get another cone of depression here. So, this is the cone of depression. Maybe you can increase these things. So, minus 5000, and just see, just solve it, you should get, yeah. So, you just see you are getting 2 cone of depression. So, that means I am getting the solution, and this problem I have solved using Excel solver. Okay. So, you can also change the plot. Suppose I would like to plot a control, I like to plot the control, that also you can do. So, insert, suppose I can see that one. Okay. I can also see the contours. Okay. So, here you can see, So, there are two cone of depression. So, there are two cone of depression, and because we have two pumping well in this case. So, the problem I have considered, so this is a problem having 100 variables. So, just to show basically that Excel is also capable of solving a problem having more variables. So, in this case I have solved a problem with 100 variables. So, you can easily solve this problem, but as I said, if the number of variable is more than 100, then you will not be able to use that one. So, it can handle up to 100, and number of constraint also it can handle up to 100. So, you can see that in this particular problem we have 100 variables and also we have 100 constraints. Then let us stop here. So, I hope you will be able to solve an optimization problem using Excel solver. Suppose if you are not comfortable with your MATLAB, or if you are not comfortable with R programming, then you can solve some problems. So, you will not be able to solve all the problem, but some problem you will be able to solve using Excel solver. Okay. So, you do not need any programming skill. So, you just define your problem and you will be able to solve using the Excel solver available in MS Excel. Thank you.